Excuse me, Mr. Vaz, I have several questions. My specialty is higher category theory, where my supervisor are Ross Street and Michael Batten.
Oh, great.
And I met John Huerta at Macquarie University.
Sorry, you met who?
John Huerta.
John Huerta, yeah, another
Yes.
student of mine. Yes. Uh-huh.
Yes. And so basically, yes, higher category theory has its own implication in mathematics, homotopy theory, etc., etc. But in physics, for me, it's I know nothing, and I am very surprised by this TQFT and extended TQFT. A few Jacob Louis, etc., many people, and this TQFT, you first speak about TQFT as a symmetric monoidal functor. Then you claim in this picture of spans, of groupoids, etc., to explain how to categorize in a direction quantum mechanics. But what TQFT, the relation between TQFT and this categorification of quantum mechanics seems for me fuzzy.
So I was talking about extended TQFTs to let us think about a situation where we have space, for example, three-dimensional space, and lots of particles in it. And particles in TQFT are little balls or disks cut out of space. And we can study that situation using the tools of topological quantum field theory. And there will be a different Hilbert space for your physical system depending on which particles you have. But in quantum field theory, we're often interested in situations where we haven't decided how many particles there are. We would like to study arbitrary numbers of particles. So that's where the Fock space idea comes in, right? So if H was the Hilbert space of a single particle, this would be a Hilbert space for arbitrary numbers of particles. So we can copy those ideas for topological quantum field theory and get we can do lots of different things. Well, one thing we can do is get a 2 Hilbert space for arbitrary numbers of particles. We can do that in the context of TQFT, in the context of topological quantum field theory. But then I wanted to sort of jump ahead and guess what kind of rules will be obeyed what rules will hold in that situation. And so I sort of look at what I know from ordinary quantum mechanics, and I say, oh well, I know that there should be operators that create and destroy particles, and they should obey some relations. And I believe that when we categorify, they should hold up to isomorphism.
And all that it is in the context of TQFT.
You could do all of that in the context of TQFT. As you can see here, I'm starting to stop mentioning the TQFT. I'm starting to just talk about what happens when you have this 2 Hilbert space H. What can you do with it? What are things you can do with it? So at this stage, I'm temporarily saying, oh, let's not focus on the TQFT. Let's just focus on what we can do with this 2 Hilbert space. But where I got the 2 Hilbert space from was the TQFT. I got it that way.
The last question.
So the reason why you're confused is because the story isn't finished yet.
Yes.
And there are lots of holes in the story. Yeah.
Last question. It's more philosophical. Thanks to you, you bring higher category theory a long time ago, 20 years ago, with this idea of physics, etc. But I think 1 year ago or 2 years ago, you have written in your website that you gave up higher category theory. And so, do you think that higher category theory can still be useful for theoretical physics, and especially to formalize M theory of Witten, etc., all these kind of very...
yeah, that's what John Guerra was working on, as
yes,
you know.
Exactly.
Yeah, no, I did not give it up because I didn't think it would work. I gave it up because I thought it was working so well that I didn't need to do it anymore. That I thought that I was not really required anymore for the success of applications of higher categories to fundamental theoretical physics. So people like Urs Schreiber and Jacob Lurie have entered this field, and they are very, very smart and competent people, and I'm sure that they and many, many others will succeed in doing this. So I decided that I should work on something else. And so what I'm actually working on, I'm not giving up on higher categories. What I'm actually trying to do, I mean, I hadn't known what I was going to do, but now I know what I'm doing. One of the things I'm trying to do is use categories and some bi-categories in applied mathematics, like electrical engineering and control theory and areas like that. Because I like to work on things where it's not quite clear that it's going to work. So I think see, physicists are talking to mathematicians all the time, so they will now know about higher categories, and that will, I think, I mean, if it doesn't work, it's because it couldn't work. But if it won't die out. I mean, people will try to get it to work. But in terms of applied mathematics, applied mathematicians are always drawing diagrams like electrical circuits and things like that. And those are really string diagrams in symmetric monoidal categories. But the applied mathematicians, by which I include all sorts of other people like electrical engineers and computer scientists, but they know about categories, and biologists and so on. They don't, so the kind of people I'm talking about, they don't really know much about category theory because they don't talk to category theorists too often in general. And so I think it's more useful for me to try to bring category theory and higher categories to those subjects now.
Just a very last question.
Yep.
Sorry.
It's okay.
Yes.
You said the last one was the one.
It's TQFT and extended TQFT, which were invented by Graham and Segal, etc. Does this tool, the Einstein general relativity and gravitation, live in this kind of things, or it's just for quantum physics? It's just a question.
Well, there are two reasons why it doesn't. So one thing is that general relativity is not purely topological in the precise sense that is needed here. So topological quantum field theory is, it sounds very impressive and fancy, but it's actually a very simplified version of quantum field theory. It's so simple that even mathematicians can prove theorems about it, whereas real quantum field theory has not been made fully rigorous, and it's much harder to work with. So, and so the theories that seem to be really important in physics are not topological theories. So that's one reason why general relativity, I don't think, will be understood using these purely topological ideas. I do think higher categories could be important. But then the other thing you asked about is classical versus quantum. So people talk a lot about topological quantum field theory. People don't talk very much about topological classical field theories, but there are topological classical field theories. So so there should be more work on topological classical field theories, and that would just be a new subject, but
for gravitation and.
Well, unfortunately, general relativity is not a topological classical field theory, but there are topological classical field theories that are like simplified theories of classical field theory. And they should be studied using higher categories. A lot of times, people work on the most fancy things instead of the simple things. So I think there should be a lot more work on classical mechanics than there is. But it's sort of considered old-fashioned. So there's not. So people do a lot of things for quantum mechanics that they could and should also do for classical mechanics.
Okay, thank you very much.
Sure. Yeah. Sure. Yes.
Is there, or have you been taking eventually cursory look at changing sets by something a bit more structured? Still being finite, which is my point of interest. Like something else, groupoids of, I don't know, colored set graphs, simple graphs.
Certainly, well, sets with extra structure actually fit into this framework. So a type of set with a set with a type of extra structure, that's what Joyal called a species. And species actually give you can think of species as living in a categorified Fock space. The category of all species is like a Fock space. So there's definitely a lot of room for understanding how sets with extra combinatorial structure fit into this picture. Then another thing is that it's very fun to take this whole story, like the story where I started using the groupoid of finite sets, and replace that groupoid by the groupoid of finite dimensional vector spaces over a finite field. So that introduces a parameter, the cardinality of the field, which people call Q. It's a prime power. And then all this stuff has an analog that depends on that parameter Q.
The groupoid is the same Q? All these objects are for the same Q?
Yeah, that's right.
Okay.
So you sort of put a new knob on the whole theory. So the commutation relations change and other things change. So that's a really, people work on that. It's a very interesting twist.
Yes? In classical physics, we choose theory of fiber bundles. We know that instead of particle wise in a group, so we consider a particle as a section of a certain bundle. Is there some analogy with what you are doing? Because I do not understand exactly the process which leads from a functor to particles. Do you mean that there are as many functors as particles, and can you distinguish between them and so on? Because when we use a Lie group,
right,
you first describe a particle by different parameters.
Right.
Can you, well, in fact, when you begin with a Hilbert space, we know that the party is over, because that's the matrix of quantum particles, and then it's not so surprising that we do not catch the mass. Yes. Where do we catch the fields? Because in fiber bundle theory, everything is clear. I know that this theory is quite new, and I do not know very much about categories.
So the problem you're addressing is that I sort of said, suppose somebody hands you a TQFT, but I didn't say anything about how you get a TQFT. And so the right way to answer your question, I think, would be to, which I don't have time to answer in detail, would be to talk about some ways that you actually construct TQFTs, and you construct them. The most important way to construct them involves starting with a group, which is the gauge group. Because these are finite dimensional Hilbert spaces, it turns out that the kind of groups you need to use are just finite groups. So If you did more realistic physics, you'd want to use Lie groups, not just finite groups. But this is, as I said, this is a very baby version of realistic physics. So if you look at fiber bundles with a finite group as gauge group, those are just called covering spaces. I mean, you might as well focus on covering spaces.
Gauge group? Gauge group?
Yes.
Gauge group.
We say gauge group.
Okay.
You say gauge group.
If I understand your lecture, you start with the Heisenberg equation, it means.
The what equation?
Heisenberg, no? Because the
Yeah.
the equality A dag A equal A dag plus 1.
Yeah.
I mean, what results will you get if you begin with another equation, with category 5, another equation?
Well, it depends on what the equation is.
Yeah, I understand that, but we all think about gravitation. There is no way to get it.
To get what? Gravitation?
Yeah.
Well,
Such a process. It seems to be generating this approach of categories as you teach it.
well, why I got interested in it is that if space-time were just three-dimensional instead of four-dimensional, then general relativity would be an example of a topological classical field theory. And then you could quantize it and get a topological quantum field theory. And so the example of three-dimensional gravity in three-dimensional space-time actually fits into this sort of framework I'm talking about. And so that's a lot of fun to study, partially because no one understands four-dimensional quantum gravity very well at all. So it's very nice to have some theory that you can really explicitly study. But there's a big difference between the three-dimensional case and the four-dimensional case. The four-dimensional case probably does not give you a topological quantum field theory. So I think we'll need some really new ideas to handle quantum gravity. Of course, string theory, they say they've got those new ideas, and it's a very much more complicated subject than I'm talking about here. So Urs Schreiber is busily rewriting string theory in the language of higher categories. And the one reason why that's good to do is that besides strings, they have been discovering that there are higher dimensional membranes that seem to want to play a role in string theory. And so it turns out that going from particles to strings to higher dimensional membranes is mathematically very much connected to going from one categories to two categories to three categories and so on. So there's this kind of big classification of string theories that people like to try to understand in string theory. And so Urs Schreiber has been showing that a lot of aspects of that you can understand more clearly using higher categories. Personally, I don't know if I am completely unsure whether string theory is on the right track or not, but it's definitely very mathematically beautiful and connected to higher categories. So, but for what's the real theory of physics, and I have no more knowledge than anyone else. I suspect it will involve higher categories, though, because I think of higher categories as pretty fundamental structures, not very unusual, strange structures, but just basically structures that you get into as soon as you start thinking about zero-dimensional things and one-dimensional things and two-dimensional things. As soon as you start drawing pictures like that, you're really in the realm of higher category theory, and it seems not at all surprising that our theory of physics would involve things like that. Yes?
So, if you replace the category of cobordism by the category of Lorentzian cobordism, for instance,
right.
What happens?
Well, so that's what you would need to do. So he's suggesting putting a Lorentzian metric, sort of like a Riemannian metric, on the cobordism. So that's the kind of thing you would need to do if you wanted to really study quantum field theory on curved space-time.
Yes.
And so
Yes.
true quantum field theory instead of just topological quantum field theory. There are people who are already working on doing that. Of course, quantum field theory on curved spacetime is a tough subject, especially for non-free quantum fields. But at least if you in the so the problem is the people who would want to use higher categories to study quantum field theory on curved spacetime, they would tend to be very mathematical people, and mathematical people want to prove theorems, so they would be limited in what they can talk about, because most of what we know about quantum field theory on curved spacetime isn't really at the level of theorems yet. It's at the level of calculations. But there are people who are proving some theorems about that, especially for perturbative quantum field theory, which you can make into a mathematical subject if you want.
And I have a similar question. If you replace the category of Hilbert space by the category of C-star algebras or von Neumann algebras or something like that, because this gives you a more general picture of quantum physics in some sense.
Mm-hmm.
So you should expect to have more results, but I don't know.
I think there are some people at least talking about doing that or thinking about doing that. I've certainly thought about doing that, but I don't know if people have really done much work on that.
A C-star algebra is an algebra of operators in a Hilbert space.
Yes.
Then maybe one category of C-star algebra can be embedded one with the two category of Hilbert space or something like that, no?
Well, there's a category of two Hilbert spaces. There are people who study things called C-star categories, which is a step towards something that you call a two C-star algebra, which I think people have thought about but haven't really worked out. So there's plenty of room for that kind of thing. I wrote a book about infinite dimensional two Hilbert spaces. So you notice I was mainly talking about finite dimensional ones. The infinite dimensional ones involve a lot more analysis, and I wound up learning more measure theory than I ever wanted to know, actually. I thought I knew a lot of measure theory because I'm trained as an analyst, but it turned out I needed to know a lot more measure theory to think about the infinite dimensional two Hilbert spaces. So there's a lot of, but we never got to the infinite. We never got to two C-star algebras, which that's just a phrase now. Hasn't been defined. So the great thing about higher category theory is you can take whatever mathematical concept you like, and you can put the number 2 in front of it, and then you have a challenge to try to see if there's a subject there that you can really study. And I think almost always, if your concept is general enough, it's a basic mathematical concept, there is something to study there. So the way I think about it is that when we're working in sort of one categorical mathematics, we're seeing shadows of things. There are these more interesting things floating up there, and we have to sort of try to guess what's floating up there from the shadows. And so that will keep people busy for a long time, I think. Maybe we should stop. You can ask me
Yes.
later. No, I mean maybe.
It is.
Yes.
Sorry.
Okay, ask a question.
Thank you, Mr. Banks.
This is your third last.
Yes. my apologize.
That's fine. It's
I
fine.
apologize. It was in relation with the question of the Mr. for gravitation, the relation itself. There is, for shift theory, there is a construction, classical construction, the Grothendieck construction from there is fiber things. And
Turning a fiber
to
category into a pseudo functor into
Exactly.
cat. Right. Yes.
That's right.
Right. Yes.
Maybe, perhaps, at TQFT, there is a kind You
wanna
can
turn
imagine
it
a
around?
Grothendieck construction like this and then find particles like section of something.
I don't know.
Yeah.
I don't know. Okay, thanks.